What specific problem does the proposed method, Gatekeeper, aim to solve in the context of model cascades?
The proposed method, Gatekeeper, aims to solve the problem of optimizing deferral performance in model cascades by enhancing the small model's ability to distinguish between correct and incorrect predictions. Specifically, Gatekeeper introduces a correctness-aware loss function that fine-tunes the small model m_s to output high confidence for correct predictions while reducing confidence for incorrect ones. This calibration of confidence allows m_s to make more informed deferral decisions, effectively determining when to defer to the larger model m_l for difficult queries. By improving the reliability of uncertainty estimates, Gatekeeper facilitates better performance in cascading systems, ensuring that m_s only routes challenging inputs to m_l, thereby maximizing efficiency without sacrificing accuracy. Ultimately, this method addresses the trade-off between model performance and deferral performance, making it applicable across various model architectures, including vision language models, VLMs.
How does the proposed method Gatekeeper work? Illustrate the methodology step by step, including its key components and their roles.
The proposed method, Gatekeeper, operates through a multi-stage process aimed at enhancing the deferral performance of a smaller model, m_s, in a model cascade setup. First, m_s undergoes standard training on the intended tasks, establishing a baseline performance. Next, in the second stage, Gatekeeper introduces a correctness-aware loss function that fine-tunes m_s to output high confidence for correct predictions while reducing confidence for incorrect ones. This is achieved by adjusting the model's predictions using a hybrid loss that combines cross-entropy and KL divergence, with a tunable hyperparameter, alpha, that balances the emphasis on correct versus incorrect predictions. In the final stage, confidence and entropy-based techniques are applied to determine whether m_s should accept a prediction or defer to the larger model, m_l, utilizing a gating function that assesses the model's confidence in its predictions. This structured approach allows Gatekeeper to effectively calibrate m_s confidence, improving its ability to defer challenging queries to m_l while maintaining overall performance.
Can you provide a simple example to illustrate how the Gatekeeper algorithm influences the decision-making process between the small model $m_s$ and the large model $m_rel$? Walk through the steps with hypothetical predictions and confidence levels.
The Gatekeeper algorithm influences the decision-making process between the small model, m_s, and the large model, m_rel, by calibrating the confidence levels of m_s predictions. For instance, suppose m_s predicts a class label for an input with a confidence of 0.8, indicating a high level of certainty. If this prediction is correct, the Gatekeeper mechanism reinforces this confidence, allowing m_s to confidently return the prediction. However, if m_s predicts with a confidence of 0.4, which is low, the Gatekeeper algorithm would lower the confidence further, prompting m_s to defer the request to m_l for a more accurate prediction. In a hypothetical scenario, if m_s predicts class A with a confidence of 0.3 incorrect and class B with a confidence of 0.9 correct, the Gatekeeper would adjust the confidence of the incorrect prediction closer to a uniform distribution, encouraging m_s to defer to m_l for class A. This dynamic adjustment ensures that m_s only makes predictions when it is confident, thereby optimizing the overall deferral performance and accuracy of the system.
What empirical advantages does the Gatekeeper method provide over traditional approaches, particularly in terms of deferral performance and computational efficiency?
The Gatekeeper method provides significant empirical advantages over traditional approaches by enhancing the deferral performance of smaller models in model cascades. Specifically, it achieves this by fine-tuning the small model, m_s, to output high confidence for correct predictions and low confidence for incorrect ones, which improves the model's ability to distinguish between easy and hard examples. This results in a deferral performance metric, S_D, that indicates a higher fraction of potential improvement over random deferral, effectively optimizing the compute budget while maintaining joint accuracy. In experiments, models trained with Gatekeeper outperformed untuned baselines by a factor of 0.70x2x on CIFAR 100 TinyImageNet and 7x10x on ArcEC, demonstrating substantial gains in both deferral performance and computational efficiency. Additionally, the method's adaptability across various architectures, including vision language models, further underscores its versatility and effectiveness in real-time applications.
How was the Gatekeeper method validated in the experiments? Discuss the datasets used, evaluation metrics, and benchmarking strategies adopted to demonstrate its effectiveness.
The Gatekeeper method was validated through a series of experiments across 3 distinct model architectures: encoder-only classification models, decoder-only language models, and encoder-decoder vision language models. The datasets utilized included CIFAR 10/100ths, Food 101, TinyImageNet 200 for image classification, ArcEC MMLU, and GSM 8K for language tasks, and VQAV2 AI2D CocoCap and Screen2Words for vision language tasks. Evaluation metrics included the distributional overlap of confidences for correct and incorrect predictions, deferral performance quantified by the joint accuracy across various deferral ratios, and the accuracy of the small model. Benchmarking strategies involved comparing the performance of models trained with the Gatekeeper loss against untuned baselines, assessing their ability to separate correct from incorrect predictions, and measuring the correlation between factuality scores and negative predictive entropy in captioning tasks. The results consistently showed that models trained with Gatekeeper outperformed their untuned counterparts, demonstrating significant improvements in deferral performance and confidence calibration.
What limitations or potential drawbacks does the Gatekeeper method have, particularly regarding its adaptability and the impact on the accuracy of $M_S$?
The Gatekeeper method has notable limitations, particularly concerning its adaptability and the impact on the accuracy of the small model, M_S. While it effectively enhances deferral performance by calibrating the model's confidence in its predictions, this comes at the cost of reduced overall accuracy for M_S. Specifically, as the trade-off parameter, alpha, is tuned to improve deferral performance, lower values lead to a significant degradation in M_S accuracy as the model becomes overly cautious and focuses on distinguishing correct from incorrect predictions. Conversely, higher, alpha, values maintain better accuracy but do not significantly enhance deferral capabilities. This highlights a critical compromise. Optimizing for deferral performance can result in M_S unlearning its ability to perform well across the full data distribution, thus limiting its adaptability in diverse scenarios.